Yeah, it's great to be here. Thank you for having me to the NZSSA. It's always good to work with you guys. It's the second time that I'm here for we talk from my perspective. I'm not a professional astronomer. I'm all kinds of things. I worked in geoscience at university overseas for 25 years, and I came to New Zealand some 24 years ago. Taught physics and maths in year 13 in Oxford area school, and now I'm way in my retirement, but I help running the observatory that we built in my days at the school. So we're the only school in New Zealand, I dare say, that has an operational observatory, which is actually run under auspices of the school. And I'm totally into education and supporting especially the young generation in raising interest in astronomy, space science, and the sciences in general. I think there's a lot that needs to be done here in New Zealand in particular. And I find awesome what the young students here, the NZSSA students, what they are accomplishing. So whatever I can do to support, I will definitely do that. So yeah, Chile. As you can see from the stylized map there, this is the actual map. It's probably the skinniest country in the world. It reminds me of a crust that's left over after you've eaten the pizza, something like that. But let it not fool you. I'd never been there before, but it's one of the most beautiful countries in terms of their landscape and their nature. I'm not an expert in that, and I've seen only the northern part of it in just only 2 weeks' time or something. It was a very short, very intense trip, but it's been a fantastic experience. And just to reassure you, I'm not going to give a talk and show all my photos, because Erik has been in Chile, so he needs to show all his photos. You know, Erik before the church, and Erik next to the church, and Erik in the church. It's not going to be like that. The theme will be astronomy. That's definitely my focus, and I understand that will be yours. I visited two of the three or almost four outstanding observatories that the European Southern Observatory is operating in northern Chile, and that in itself has been a fantastic experience, and I really like to share that with you guys. And secondly, I've spent some time in the northeast, the far northeast of Chile. There's the Alma Observatory, but I didn't go there. There was no time. But I want to share some of the absolutely astonishing landscapes that you have there and the geophysics behind that. So that's the end of my talk. How did it come about? So yeah, those were the highlights. La Silla for the Eclipse. La Silla is one of the observatories. I'll explain that, of course, at length. Paranal is the other observatory where I was, which for me was the highlight, personally. And then this Atacama Plateau. But first, why did I go there in the first place? As it happened, the eclipse of the 2nd of July this year passed over Chile. I'll show you a map in a minute. Over Chile, but over the La Silla Observatory. And ESO recognized that, of course, years ago. Last year, they let us know via their newsletter that they were going to organize an eclipse day on the mountain, on La Silla. But they were selling only 300 tickets. So it's kind of an exclusive thing. And I was going to say something else, it doesn't matter. But anyway, that's, yeah, and of course, the La Silla has its 50th anniversary this year as well. So that was another incentive for ESO to organize this. They announced last year that they were going to sell 300 tickets. And I had the impression, or expectation, because it's worldwide, that they would be sold out pretty fast. Like a rock concert, you know, for a famous rock star, one performance only at a particular venue. They sold out in 10 minutes or something. I expected something like that, but I wasn't sure. But I definitely wanted to go, and because the combination of an observatory and the eclipse, and then going to Paranal as well, that was enough for me to really make me totally excited. I'm not an eclipse chaser by any standard. It's only my second solar eclipse that I've seen. The first one was when I was a secondary school student in the Netherlands. It just happened to come over where we were. So I have vague memories of that. But and there was another personal reason. In addition to that, I have a daughter in Spain. She lives in Spain, so I don't see her very often. I took her to a StarMUS conference once in Tenerife, which I don't know if you've heard of the StarMUS conferences. They are every other year, roughly. Stars Music, that's where the name comes from. Brian May, he is the guitarist in the Queen group, he is an astrophysicist. He organized and he still organizes StarMUS together with his promoter. Anyway, so we were there. My daughter was, she is not in professionally or so in astronomy, but she was really excited. And I was thinking, before I knew this possibility, I was thinking of going to the StarMUS in Switzerland this year with her. And but then this came up and I asked her, do you want to come to Chile for the solar eclipse? Oh yeah. So for me personally, that was definitely the landslide reason for me to make this happen. So there's a lot of incentives for me to do this. Now ESO is the European Southern Observatory. They are an organization. They are supported by 16 European member states, as you can see. And what they do is, don't confuse them with ESA, which is the European Space Agency. That's the equivalent of NASA in Europe. Of course, there's a lot of overlap, but what ESO is doing is develop instrumentation and build and run observatories to promote the science of astronomy. I think it's a brilliant initiative. I want to make a sidestep here, especially talking to the young astronomy students here. I had about 4 or 5 years ago a discussion with John Herschel. He was the president of the Royal Astronomical Society of New Zealand at that time. I was representing the education group of the association. And I saw that ESO is doing all these things for young people, space camps like NASA is doing, scholarships, what have you. And I asked him, why can't New Zealand become a member of ESO? Then our young people are exposed to those opportunities as well. There was a whole discussion. He put me on to somebody by email at ESO. But I came back to John, and then he said, yeah, but ESO is the most expensive astronomy club in the world because they charge 100 euros per year for membership. I didn't believe the M, so I asked him, what do you mean? He said 100 million euros membership per year. So that was the end of that discussion. He said, I can't even get 1 million for Mount John, which would be really necessary to make it the national observatory. That's one problem we have here in New Zealand. Later, I went back to the ESO website, and also if you click on the link here, the 16 members, you can see what each of those members are paying annually, and it's far from 100 million. It's a lot of money. Germany and France are paying the most, which is about 40 million euros per year. The Netherlands, where I come from, is a founding member. They pay something like 8 million per year. It's a heck of a lot of money, but the spin-off is, of course, that your local industries in those countries, that they get access to offering or bidding on contracts, because they do a lot of instrument development at really frontline. So if you can, if you can meet that. If you can meet that requirement, then your country is well off, and it's just a good investment. The other side is doing the research. They do, astronomers in those countries, they do absolute frontline research. They use these observatories, they get observation time on these observatories. So I'm still thinking, but that's long term, that New Zealand should think about eventually becoming a member of ESO, if there is enough infrastructure and interest within the country, and I think that's one thing that's lacking. You organized a panel discussion, I think, some time ago with Space Base together about this growing space industry in New Zealand, which is really important. I would suggest to extend that into the technology that you need to build equipment and instrumentation at top level. Optics, I don't think we can compete. There are only a few countries and even companies in the world that can make real good optics. Germany, France, That's about it. But everything else, the mechanics, the engineering, the IT, whatever, I believe that New Zealand could grow into such a direction if that would be a political decision for it. And the same thing for the astronomy side, to do real frontline research with the top-notch observatories in the world. And so that would be the spin-off if you as a country become a member of ESO. I'm not promoting this on behalf of ESO. I just feel very strongly that I think we need to think outside the box, especially the younger generation towards the future. What do you want? Where do you want New Zealand to go? And I think that's really an important thing to kind of keep in mind. There is a precedent. You don't need to be a European country to join ESA. Brazil expressed years ago, that was already at the time that I had the discussion, to become a member. I've just recently looked it up and there's something is hanging. I think Brazil cannot make the final decision. It may be a money thing, I don't know. But the precedent is there that ESA would welcome non-European states to be a member of ESA. Anyway, that's what I wanted to get to talk to you about. You see on the, I'm not sure if I can switch on the pointer. Yeah, you can see our pointer.
Was it those telescopes that were watching or finding that giant black hole?
No, that is the Event Horizon telescope you talk about. No, Alma Observatory, which is the top one in here, those three red dots are the main observatories that run by ESO. This is Alma, which is a millimeter astronomy array. They are absolute frontline in that frequency, in the millimeter wavelengths of radio. They do observations of protoplanetary disks around young stars that are just forming. They can find planets. I mean, in there, they have an amazing resolution. They were part of that Event Horizon telescope, but the rest, I'll talk about Paranal in great length and show some of the research that's going on there. But that's standalone. That's not in this worldwide Event Horizon telescope. Anyway, you see here in the north of Chile, this is Santiago, by the way, the white dot. Here you see the three main observatories that are operated by ESA. This is La Silla, where the Eclipse was. This is Nal, and this is Alma. And we'll get close to, I'll visit those two with you, and I'll get around in this area. I need to know which button to push. So the Eclipse, as I said, they sold 300 tickets. I was really, for the reasons that I just explained, I was really keen that I had to go. It was on a particular date last year, July or June last year, and it turned out that the time they had indicated in European time was 11 p.m. here. So 10:30, I sat at my computer and I knew which page to go to on the ESO shop website. And I refreshed the page and I got the message that and that date, that and that time. So I thought, well, maybe they are going to be really precise at 11, or we'll see, and it's going to be a long night for me, but I wanted to get 2 tickets. And I kept refreshing the page. The 1 minute before 11, every 30 seconds or so. And lo and behold, exactly at 11 o'clock, I got the booking form. And of course, I filled it in the details. That took some time, the credit card, you have it. And I submitted, and I got a minute later, I had an email confirming, so I was in. Just out of interest, I went back to that same website. That must have been 10 minutes later. And I got server not available, try again later. It was clearly overload. So I was really, I did the right thing to be there first, basically first in line, and really determined to get a ticket. I couldn't get in after, I didn't try too much because I knew that I would be hindering other people who were still chasing for tickets. At 11:20, I tried once more and I got the message, tickets sold out. So they sold out 300 tickets in 15 minutes roughly, and they made 60,000 euros because the tickets were 200 euros each. It's not cheap. I grant them that, but and they did a fantastic job in organizing the eclipse. So here you have the. This is the eclipse path this year, 2019. It started here in the Pacific. Most of it was in the Pacific. Only in the afternoon the shadow made landfall in South America, mostly Chile, and then into Argentina until the sun set. So for us, it was going to be an afternoon event. Do you all know about eclipses, why they happen and when they happen? Do I need to explain anything? If you have any questions, please ask, okay? I'd be happy to go into some detail. But a solar eclipse typically, and that's what you see on this map, has a very narrow ground track on Earth, on the surface of the Earth, where you can actually see the total eclipse, where you see the moon in front of the sun. And the sun's completely blocked out. It's what we call a total eclipse. And that track is somewhere between 200 kilometers wide maximum, and it can be smaller. You see a little bit on this map, but the width is varying. There's also a map projection problem here. This one was about 200 kilometers wide, the track. And I can show you. This was a map they had. This is a town called La Serena. That's where we had our accommodation. The red dot I put in this map is La Silla Observatory. This here is the width of the shadow path. So we were just north of the center line. And La Serena, this it's like a historic port town, was a bit south of here. What else were I going to say? In addition to the, we were talking about the eclipse. So you need to be in that ground track to see the total eclipse. And that was, of course, the fantastic opportunity that ESO grabbed, that one of their observatories was right in that shadow track. It was really well organized. You would expect it for 200 euros a ticket. But I'm not complaining at all. It was really worth it. We got lots of information beforehand as well. Also security. We had to watch a video online before we traveled. We had to sign a Google form that we had watched that video. They were really serious about their security. They had said that in addition to the 300 tickets for people, for the paying guests, they would have additional groups, mostly from Chile, invited, and some hotshots for the VIPs and media. So the total number of people on the mountain would be something like 1,000 people. So it was going to be busy. This is the route, mainly highway, the Panamericana Norte, they call it, the highway all the way to Asca. And there was an exit to the observatory, but they told us, no, don't take that exit, take the next one, which is a dirt road, because on that exit to the observatory, the road, in the middle of the road, they were building, some people were building a whole camp of eclipse chasers. So that road was blocked. So it worked exactly as they told us. And this was when we came closer, the observatory there on the mountain. As you can see, it was a brilliant day. Even at sea level, we left from sea level. There was a bit of hazy clouds, I think, but when you got up higher, it was absolutely brilliant today. In many instances, people who want to watch the eclipse, the big nervous thing is the weather, if it's going to be cloudy. Here, there was absolutely no concern. We didn't even think about it. It was just, and especially when we were up top. This is right on top of the mountain. Fortunately, it is a very large observatory, so these 100 people, as you can see, or you get an impression at least, that they could easily accommodate that. And there was one ridge, which you see here, the length of, that was facing the northwest, and that's where the eclipse was going to be, and we had a free view over the mountains in that direction. So it was really awesome. They have lots of telescopes there. Some of them are decommissioned, so there's a whole history of 50 years. Two main telescopes, I think, and they were the ones that were open for visits, at least theoretically. was the New Technology Telescope, which was, they say, the first one that had active optics, which means that you have pistons under the primary mirror that can reshape the mirror to accommodate for distortions because of weight when the telescope moves, or temperature, or whatever. Anything you can model, they can compensate for that, what's called optics. ESO claims that they invented that, and that is the first telescope that had that set of technology, which is now widespread, of course, major observatory. And then they have the 3.6, which is famous at the moment for doing exoplanets research, the radio velocity method. They have the very famous HARPS spectrograph, which apparently is a bit of a top-notch spectrograph to measure the shift, the red and blue shift of the star in the radio velocity. I have some pictures. This is the overview over the mountain. So we were here along this ridge. It was actually a very good layout for that, because it was facing in the right way. This is the NTT here. You can see this is a restricted area for VIP media. I'll explain that we didn't get into the telescope there. This is the big 3.6 meter here. These are Swedish, the Swedish telescope that's decommissioned. I tried to get to the NTT. That was really, in addition to the Eclipse, that was what I really would like to see. I must say that was not really. Sorry, I should talk in here. That was really the only thing, in addition to the eclipse, that I was really interested in. I was still really tired. It was a few days after we arrived, and there's a 16-hour time difference, and I'd been teaching courses until 2 days before we left, or I left. I was really exhausted, so I didn't feel really well at that altitude either, 2.4 thousand meters. But anyway, the NTT was something that we wanted to have a look at. But my daughter, I didn't do the walking. She went there, and before lunch, no, I was too busy, too long lines. Maybe during lunch, we are closed for lunch. It was against the program they had published to be open, but it was closed. After lunch, no, sorry, we have a media event. So, okay. That was it. I haven't seen any telescopes near from close up there. But anyway, the solar eclipse, of course, was the real important thing. Oh, this is a close-up picture. This is from an ESO picture of the NTT. And the other one, we took this picture because we were standing right at the bottom of that ridge. So, yeah, I call it a disclaimer. I'm not an astrophotographer. I have no fancy videos or photos to show you. That's not the incentive of this talk at all. I'll show you what I have experienced and a little bit of what I've done just with my phone. And on a tripod, I made a time lapse. That's the only thing I really did. And so I'll show you that. But there's nothing fancy. But I have read many stories about people who witnessed total solar eclipses, and the same thing was said over and over again, especially the people who came with a lot of gear. They regretted deeply after the event that they had spent so much emphasis and time on their equipment. Does this work right? Is this setting okay? And they forgot to watch the whole thing and to experience the whole thing. So I knew that definitely that was not me. I was going to watch and experience. And I cannot say anything else. That it's a deeply emotional experience. Absolutely. I'll come back to that. This was probably during the partial phase already, because this guy, my neighbor, had his glasses on. You can see how busy it was on that ledge. This is a panorama of the whole view that we have. Fantastic view over the mountain. So as a location for an eclipse, it couldn't be better. That is just bonus. Absolutely fantastic. You can see the sun is somewhere here, and it was going that way, of course. So yeah, that's how we prepared. These are the times that we knew, of course, and these are very precise. There's no doubt about that. There was a bit of how do you say it in English? You live up to that moment that it starts, that you can see that the moon is biting into the sun. That's of course an interesting point. And hey, I think I can see something at 3 o'clock. No, I see. You never had those discussions. And then at some point, yeah, okay, now we see it. Definitely, it was. What was it? 7 o'clock. You saw definitely the moon coming in. But then I must say, it lasts more than an hour, 1 hour, 16 minutes. The partial eclipse is hardly of any interest. You have this initial excitement, but you don't see anything else. You have your eclipse glasses, and you can see it. But with the naked eye, you can't see any, you can't look into the sun, it's far too bright. You don't even see the ambient light change very, very much. Only when the partial is way above more than half, I would suggest somewhere 70, 80%. Then you start to see the light is kind of dimming a bit towards as if it were becoming dusk, you know, that kind of lighting, only at that final stage. And then there was the final stage that with the eclipse glasses, you could see a really thin, very bright rim of the sun. And I said, well, it's going to happen anytime now. We looked at the clock and it was still 2 minutes to go. So this is a really slow process. I'll show you just a couple of photos we took with my or my daughter's phone. This was actually way just after the totality. So this is a partial eclipse. You can see that the light is really dim. This is 80, 90% coverage of the sun. That's the kind of lighting you have. But if you take a photo, there's no way that you can see the moon in front of you. You need a solar telescope to make that visible. I've seen others with much better cameras. You can't. You need a solar telescope too, and maybe Rob you're the expert, can explain what you need to make that visible. But with an ordinary phone, it's over-illuminated, overexposed. You can't see that. I also tried the photo through the eclipse glass as a filter, and this is what you get. It looks distorted, but it's not the moon that you see here. This is just a distortion, because this is not the shape that it was. So you can't photograph it. Anyway, we had a good time trying those things, and we had plenty of time, of course, towards totality. And then what I call is a sledgehammer effect. So you have very, very thin sliver of sunlight, but it is really bright. You still cannot look into it with your naked eye. The slightest amount of sunlight that comes directly past the moon is really too bright. And then all of a sudden, it's like somebody flips a switch, a cosmic switch. Then it turns dark, really, really suddenly. And that is a deeply emotional experience. I got tears in my eyes. My daughter started crying. We hugged each other, and you hear the uproar from all the people around you, the whole mountain, you know, whatever, 1,000 people. You need to do something with emotions. You make noise, and yeah, this really is a sledgehammer. I think it's a good expression. This is one photograph I took, which actually is, I'm very pleased with it. The circle you see around the moon is far too bright. This is overexposed. You can easily look at it with your naked eye at that moment when it's total. Don't even think about it. And you see the corona with a thin line. This is just overexposed. I'll show you some other photo from somebody with a better equipment who has a slightly better version, but you will probably always get that. The other thing which immediately struck us as blowing us away was the color on the horizon. As you can see, all the shades between orange, red, yellow, pinkish, purple, you have all these colors right there. And that happened at the same flip of the switch. It was really like that. Sorry?
Which way? Which compass point? North, south, east, west? Which way?
This is northwest.
It's facing northwest.
Yeah. Sorry, what say you? Yeah. Venus is here somewhere. Oh, I can't see it on my screen here. Somewhere here was Venus. We could also see stars higher up. We could see stars, and Jupiter was there as well, if I recall. But definitely Venus was very clear. Oh, it's here. This here is Venus, yeah. But those colors are absolutely mind-blowing. And this is a frame out of the video I took because it was fun that my daughter was, she wasn't aware that she was standing in front of my camera. All the immersion, and she took the photo of the eclipse. So you see the eclipse twice here, you see it here, you see it. This is already towards the end of the eclipse because you can see that the horizon gets whiter. So the shadow in the distance is already retreating. Shadow is coming our way. The obligatory selfie, what this shows is the fact that the light is really dim at that time. Sorry?
Lights, shining on the screen.
Can I do this here?
You can only turn on the one camera. Let's do that.
It's okay, I don't think mine's stream. We can use audio.
I need to switch off my point. This is my laptop, my time lapse. And I slowed it down 50% to, otherwise it would be only 17 seconds. You see the camera is adjusting for the light level. That's the flickering you see. Bingo. There you have the total eclipse. You see the color. You also see that we are north of the central line because on the right-hand side, which is north, you see more bright sky. That's where there is no shadow. And then you see the horizon in front lighting up gradually. That means that it's becoming the end of totality. That is the, how do you call it? The diamond ring effect. Anyway, so that's all I have. About the diamond ring effect, that was really, really visible very clearly with the naked eye. First, we saw a sliver of red light around the moon, which is the chromosphere. I remember saying to people around me, this is the chromosphere, we can see the chromosphere. It lasted for maybe 5 seconds, I don't know, several seconds. And then you had this sudden explosion, kind of a pierce of the diamond ring effect. That's the first sunlight which comes through craters, between craters on the rim of the moon. So the first direct sunlight that hits you, that's what is referred to usually as a diamond ring effect, and that is really spectacular. You could still look at it with the naked eye, but only seconds later there's more light coming, and then it becomes really blinding, and then you are back to a partial eclipse, basically. I'll show you just a few photographs that other people have made, who are much better than I am. This is ESO itself, they published this one. So this is on the, you see the whole, most of the observatory here. Behind this ridge, that's where we were standing. So this is the 3.6 and the NTT is behind there somewhere. But this is the diamond ring effect, more or less. It's that moment that they took this picture. And you still see that there's a fairly bright ring around the moon, and that's not what you see. This is overexposed. Otherwise it would be an annular eclipse, then it's totally different. They published this a little bit later. This is, of course, through a solar telescope or a proper camera. You see the chromosphere here, and you see, sadly, this is a little bit too late. If they would have taken an early exposure, you would have seen the real diamond effect, which is just one spot of light right here in the center. This was already when it was kind of blinding. And this is horizontally flipped, because I know for sure it was, this happened on the, what was it, 4 o'clock, 4 or 5 o'clock, but it doesn't matter. And then I found on Facebook the next day, Mark G, he is one of the best astrophotographers here in the country, in New Zealand, and I don't know him personally, but he published this on Facebook. This is low resolution. So he was in La Serena, this is La Serena. He was probably from his apartment or something. And he won't publish high resolution products because he does it professionally. He makes a living out of that. So He published a little bit later, he published this photo of the totality. Surprisingly, we could see he could see prominences, although the sun is extremely low in activity at the moment. Let me see if I can go to this video. Need to switch off the pointer. It's basically the same what I've done, but a lot more better quality, a time lapse of the whole thing. I'll start again. It was 2.7. He was somewhere south of the center line on a mountain. I don't know who it was. I don't know his name, but he was at a very good location on a mountain somewhere, he told, and he described. And there were hardly any people there, so he was really enjoying this. Here you see the light coming from the left. From the left. So he was south of the center line. But very similar to what we saw. He was on a high elevation. Okay, let me get my my stuff right here. Okay, then I'm going to talk about Paranal, which for me is the highlight. Actually, we first went to the northeast. The solar eclipse was on a Tuesday, so the next Wednesday we traveled to the far northeast of Chile, to San Pedro. I'll come back to that. Because we had time to spare. Paranal, we did just the normal weekly public tours that they offer. Every Saturday, if you ever go to Chile and you want to see Paranal, every Saturday they have a morning and an afternoon session. And you need to book in advance, and then you can just go in, it doesn't cost anything. So we had booked the Saturday after the solar eclipse, so that was actually the end of our trip, but I'm going to talk about this now. This is the entrance of the driveway, but it's many, many kilometers long, the driveway. It's really kind of weird. You expect a tall mountain somewhere with a major observatory, and you see those relatively low hills, so it must be somewhere behind. How come we don't see this? I think the reason is that we are already at significant elevation here, and this was a very long driveway all the way around the mountain here, and we had to go around, and then at some point we definitely saw the observatory. Just about the location, it's south of a city called Antofagasta. It's a main industrial port city. We stayed there, and it was, 1.5 hours driving. Talking about driving, I bought a SIM card at the airport when I arrived in Chile to have a local phone and be able to do GPS and things like that. But it was more or less a waste of money because it only worked in Santiago, and in the country, sometimes it worked, sometimes it didn't. We did most of the navigation driving the old-fashioned way. Because of the distances, we flew from Santiago the first day to La Serena, to the Eclipse. Then we flew to something up north to go there. And then we drove a car to Antofagasta, and then after Paranal, we flew back from Antofagasta to Santiago, so that we took flights, domestic flights, and local car rental. We needed to do that because we had very little time, and the distances are fairly large. So anyway, this was a relatively easy drive. And then when you go along the driveway and then turn a corner, and you clearly see that you have reached Paranal. I have talked about Paranal in my courses a lot, and I'll come back to that. And I have seen so many videos and things. So I immediately recognized this. This is the very large telescope, the VLT, that you see, the Ford telescope. Anyway, so wow, we are there. It's 2,635 meters elevation. So it's only 200 meters higher than Silla. But because it's so extremely dry, dry is basically the main reason that they are in Chile in the first place. The whole north of Chile, the Atacama area, is one of the driest places on Earth, especially for infrared. That's an essential that you have as little humidity as possible. So at that location, they have absolutely fantastic conditions. This is an ESO photograph to give you an overview. The VLT, the Very Large Telescope, is composed of 4 identical telescopes. You see them here. This is a survey telescope. It has not directly anything to do with the interferometer. They work as an interferometer does for telescopes. They can create a synthetic image as if the aperture of the telescope is much larger than one single telescope. That's the principle of interferometry. They also have these auxiliary telescopes, 4 of them, smaller ones, and they move on tracks, and they have many predefined positions where they can anchor them precisely. And the ensemble of the 4 main telescopes plus those 4 auxiliary ones, depending on how they configure it, they can form a baseline of something in the order of 140 meters. So the resolution they get is the same as if the whole telescope would be 140 meters diameter. That's really the trick with this interferometry setup. This is one of the main observatories in visible and infrared in the world. There are basically 2 locations in the world where you get really that kind of quality. It's in Hawaii on the Mauna Kea ridge, the volcanic ridge. Mostly the American institutes run their telescopes there. That's top notch. And the European Southern Observatory does it in Chile. These are very comparable locations in terms of the quality. What you can see is that the mountain is really limited in size. They just can fit those 4 telescopes and a little bit of other stuff on there. That's the only flat area. Stark contrast with Silla, where they have all kinds of space. Just an overview before I go into the details of the VLT. An overview of, this is a security map actually, but it is a good plan of the whole observatory. This is the top of the mountain. So you see the 4 unit telescopes, is the VLT here, as they call them. These are the auxiliary telescopes, those tracks. This is the survey telescope. This is Vista, which is on another hilltop. I didn't know those things. I found it out after when I make this presentation. I wasn't aware. The focus of this public tour was only the VLT, that was all. But on an adjacent hilltop, you have the Vista here, the survey telescope, and you have 2 robotic systems for exoplanet search, next generation transit telescopes, and a ridiculous name, Speculos. Let me show you the text. So the survey telescope, that's a 2.6 meter. It has a huge camera. The survey telescope is something that scans the whole sky in the shortest possible time, night after night after night, continually, just to find things that are moving, things that are outliers. It's asteroids or anything else. This has a 268 megapixel camera. Then this one here is the Vista, which is a larger one, but has a smaller camera in terms of resolution. And then you have the exoplanet search robotics, 12 20 centimeter telescopes in one housing, which is up here. And then Speculos is run by the University of Liège in Belgium. They say that they have found this mnemonic for referring to a suite, that I'm from the Netherlands and we have a specific Dutch delicacy which is called speculaas, which is instead of the double O, it's double A. Maybe these French-speaking people in Liège are confused with it, I don't know. But it sounds really fairly ridiculous. Anyway, this is a fully robotic system for 1 meter telescopes, and they run, of course, continuously. So nothing then positive news from them. I just wanted to make fun of the name. Okay, so the first thing, I need to go back and show this. Relatively shortly after you get to the entrance, this is broken up here so it's not to scale, you have a parking where we stopped. We were taken up by couches, buses. There were maybe 400 people or so, maybe a little bit less, 250, 300. It was really crowded. This here is the famous Residencia. That's the hotel where astronomers can stay, and anybody working on the mountain can stay. This is an award-winning design, I'll show you. And you have service buildings at that same location, the same height on the other side of the road. And then the bus took us up a much longer trip, all the way up to the mountain. So let's first have a look at the Residencia. You may remember that you've seen this or seen pictures. This is an ESO photo we couldn't get on this side because you would have to walk. We were really on the other side here. This is the entrance on this side where the mountain is. We didn't have the time to walk around, but it wouldn't allow us at all. It wouldn't be allowed as well because you would have to go into the countryside away from off the road. But anyway, this is the famous Residencia. It's an award-winning design. This is from the parking area. This is the main entrance, and I cannot walk stairs very well. So this was, to my delight, it was just a ramp. You see the dome, which I will show you the inside in a second, and so that is the main area. So this is the way you walk in. This is inside. So we walk in here, and then behind me is this gallery around the wall, the outer wall. It comes down here, and then it becomes horizontal. We were allowed to go till here. There were people having breakfast or coffee or something like that there. So this is really the recreational area. There's even a swimming pool. And then in both directions, you have the actual residential areas, the hotel facilities for quite a number of people. If you looked at that earlier picture, they must be able to accommodate quite a number of people there. If you have seen the Quantum of Solace, the Bond movie, you'll recognize this. This was partially shot, and that made it famous at the Residencia. This is the Bond girl running for killing the general who was sitting there somewhere. Anyway, let's go up to the top. So the VLT, very large telescope, are 4 telescopes of 8.2 meter main mirrors, and the auxiliary telescopes are 1.8 meters diameter. In interferometry mode, the whole ensemble together, as I said, can provide about 140 meter baseline with a milli-arc-second resolution. This is a photo we took ourselves, a panorama photo up top. You can see the people walking here. I think I'm here. For the scale, how large these buildings are. The names of the 4 telescopes are basically unit telescope 1, 2, 3, and 4, but they have Mapuche names as well in honor of the indigenous people. The Mapuche Indians are the most recent Indians that were there when the Spaniards came in, so about the same time as the Incas. So those are the 4 Mapuche names of the telescopes. This is in close-up of one of the auxiliary telescopes. I really like the simplicity of this design, that just with a simple piston you can open the dome in 2 halves, and then you have the horizontal opening, I guess. I haven't seen them open, but that's what I guess. It's a really simple design. He's a really nice guy. What am I doing? Okay. So this is, with the elevator, you can go into the telescope. This is the building of telescope number 1. And there are 2 levels. We were at the top level here. You can see it here, and this is the ground level here. You see this ridge here, the gap, that goes around all the way. And everything inside that gap is rotating with azimuth. The whole blooming thing is rotating in azimuth. So if you stand there down, you will rotate with it. And he told me, and I can understand that this is, of course, mechanically very well designed, that one person can push the whole thing around. Of course, it's done electrically. Anyway, you can see the width here of the whole building and the telescope here in the center. This is a vertical panorama. You can see the whole telescope. This is the mirror. It's 8.3 meters. It's one point piece of 0 dur. It's rounds with a zero thermal coefficient. But it's one piece, and he said it is 17 centimeters thick at the edge. You can also see the distance there for the active optics. It's supported with a whole field of these distance. There's a secondary mirror up here, and there's a tertiary mirror in the elevation axis. It's an azimuth elevation setup. Close up of the elevation axis, and that's where the whole detector packages are. I think in the previous one you can see that these are all, yeah, don't ask me the details, but this is all detector stuff. There's a vessel here with liquid nitrogen or helium, I don't know, for cooling. And then we went downstairs on the floor, and you can see at the bottom you have the, they call it the Cassegrain detector package. Because if they flip the tertiary mirror away, it becomes a Cassegrain telescope, and you'll focus at the bottom. So they can use the telescope standalone as well, in kinds of options. I want to go back to this one here. He told us that this is an 8.3 meter diameter block of 0 dur, this mirror. They can, and it's designed that way, they can shift it outside, they take it out like a pizza out of an oven, out of the telescope frame, through an opening in the wall, outside, or will be wrapped up, of course, in a casing. On a truck, drive it down the mountain, where they have the facilities, and they have one building where they can resurface the mirror. Completely resurface it. They do that every 18 months, with each of the 4 mirrors. It's an amazing thing. And he said that the telescope is out of operation for 1 week when it happens. So this is a really well-designed system of resurfacing the mirror at that frequency every 18 months. Amazing. I'll show you the outside in another picture in a minute, where you can see the opening. Okay, that's about the auxiliary telescopes. You have seen already a close-up. And here's a close-up of one of those pre-designed positions where they can anchor it for whatever configuration they want to do. Now we get into the instrumentation, and I have taught a course just last term, and I've written the course as well. It was a very hectic time for me, but amazing. But I taught a course exploring the Milky Way. I talked about the Milky Way galaxy. And we spend a lot of time on the center of the Milky Way, because that's where exciting research is happening right now. And I came across, and that's the reason why I'm so utterly excited that I've been now at Paranal, because they made 2 major accomplishments just last year in terms of confirming general relativity to do with the center of the galaxy. Gravity is the instrument, which is a spectrograph. Well, it's far more than a spectrograph. It does delay lines with fiber at light wavelengths, accuracy and things. It's I can't give you any details. It's an extremely complicated system. I read about it, but I showed you a photo. It doesn't say much. It can image in the interferometric phase with 4 milliarc seconds. But amazingly, it can do astrometry, which means measuring position of an object to microarc-second level. And this is what they used for this accompaniment I'm going to talk about. Before they go there, this is a really wonderful infographic, ESA, which shows all the various instruments that are attached to the various telescopes. I hope you have time, because I'm talking so much. Is it okay?
Yeah.
I really like it if people let me talk without having to look at the watch all the time. That's awesome. I don't know if you can read this, but so you have each telescope has its own package of various instruments. But the gravity is one of them here, which is in this building here. This is the interferometer building, they call it. This is the building from outside, and called me a silly old fool, but I was really emotional when I was standing there because I realized this is as close as I get to gravity, to that instrument I've talked about so much. Oh yeah, here you can see the opening in the dome building, in the telescope building, where they slide the telescope out and onto this frame, and then it will be picked up by a truck or something and then taken down the mountain. So that's where the mirror comes out every 18 months or so. This is gravity, it's an ESO picture. Of course, if you want to see equipment, it's always built in a container for conditioning and things like that. If you go to Mount John, you want to see the Hercules spectrograph, they will show you a similar container. You would have to go there when they do maintenance and you can see the stuff. Anyway, it's, I'll talk about what excites me so much in terms of the research that they did last year, and then you hopefully get an idea why I'm so excited. They had two major breakthroughs last year, and that was they observed for the first time in history a phenomenon called gravitational redshift, for which you need a really strong gravity field, like it's impossible to observe. And they also have got indirect, it was a lensing effect, flashes that were caused by gas clouds that are rotating at 30% of the light speed around the black hole in the accretion disk at the closest possible range. Those are the two things that happened just last year there in Paranal. Before I'm getting carried away in those topics, let me remind you that this year is 100 years since the first confirmation of general relativity, Einstein's general relativity. That was in 1919, with a solar eclipse. We celebrate Apollo 11, 50 years, with all the, I'm not saying anything against it, it's fantastic. But this year is also 100 years since the first confirmation of Einstein's general relativity. This is a front page from the Illustrated London News from November 1919, where actually a fairly good infographic, we call it nowadays, what they did. There's a guy called Arthur Eddington. He was kind of instrumental. He wanted to prove or disprove general relativity. It was only 4 years after Einstein had published his paper. During a total eclipse, you can see stars around the sun. And the prediction, of course, of general relativity is that space-time is curved in gravity, because of gravity. That means that light bends. If you are in a sufficiently strong gravity field, light should follow the curvature of space-time, it should bend. And this is indicated here in this graph. So the star is actually there, but you would see it here. So what they did is they took photographs on photographic plate in those days of these stars around the sun during totality, and then they compared that, they overlaid it with the same photo, or the photo of the same group of stars, but then taken without the sun, so at night. And then you should see a systematic shift of the stars between the two plates. The further away from the sun, the lesser the effect would be, the closer, the stronger. Lo and behold, they did the analysis. The eclipse was in May, 29th of May. They had observatories in Brazil here and in Chile, that is a small island of the African coast. And they totally confirmed general relativity. It was spot on what Einstein had predicted. And this really put Einstein on the map for the general public. He wasn't really well known before that at all. In scientific circles, yes. But this event and the publications, it was worldwide. This is just the London News in the US. All the newspapers were doing a similar thing. They really put Einstein, they made him famous. Okay, that's a bit of history. For about 25 years, several groups in the world have been studying the center of the Milky Way galaxy. And
they have found stars that are orbiting in proximity to the what was supposed to be or expected to be a supermassive black hole. Of course, you can't see it, but these orbits are all going around the same point. This is research that has been going on for 25 years, more than 25 years now. There are two main groups in the world. It's the UCLA, the Galactic Center Group, and in Germany, at the Max Planck Institute for Extraterrestrial Physics. The latter, the Max Planck Institute, is of course connected to ESO. The research I'm going to talk about was run mainly by the Max Planck Institute. There's one star that has an orbital period of 16 years, called S2. They observed closest approach to that focal point, which is invisible, in 2002. So it was due for the next one in 2018. And that's what they were prepared for. Now they have that gravity instrument with its ridiculous astrometric pointing accuracy of micro arc second level. And that's why they got this accomplishment, because what they observed was what is called gravitational redshift. This is just an artist's impression, of course, but with gravity, I've read articles about this. They could, from night to night, they could see the change of the position of S2. That's the resolution that they have. And gravitational redshift is that in a very strong gravity field, if an object is moving away from the center of the gravity field, so it's flying out of the gravity well, so to speak, it is stealing, as it were, energy from photons that are emitted by that object. That means that it's a reddening effect, it's a redshift. That's the best way I can explain it. I'm not an astrophysicist, so, but that's the principle, and this is totally predictable by general relativity, but it has never been observed before because we never had the instrumentation to do this. And this gravity instrument in particular made this observation, and they confirmed that they saw redshift. I hope you'll have time, because I really would like to show you the 7.5-minute video on ESO. Sorry? How much? 10 minutes? Let me try. This is I'm almost there, and the last part about San Pedro is really short. So
Yeah, we can keep
I'll go there.
15 minutes and then we'll have more time for questions. So it's on.
Sure. Yeah. This is a video you can find on the ESO website, and it explains this particular experiment I've just talked about, and you can see the actual people who are involved. This is a major breakthrough where we have observed what's called gravitational redshift. There are 3 forms of redshift, very basic. The simple redshift is the Kepler effect, the Doppler effect, sorry. The Doppler effect, where if some source is, if the race car is coming towards you you stand along the racetrack, it's a high pitch. It's going away, then it's a low pitch. You only hear the right frequency if it's at the closest point, closest approach. But that's the Doppler effect. In light, that works as well. So you can measure the radial velocity of stars or galaxies by the shift of the wavelength, the spectral lines. If you look at our Andromeda galaxy, you'll see that this blue shift, that the Andromeda galaxy is coming towards us. Then you have cosmological redshift, which is due to the expansion of space itself. It's at very large distances. The actual relative velocities don't count anymore. It's the expansion of space which takes over. That's called, there's a Z index, which actually is a measure of distance because of Hubble's law. And then this gravitational redshift is the 3rd form, which is only happening or measurable in an extreme gravity environment, and that's what they just did. This is the 2nd one. This happened in October last year. I'll be very brief. This is the artist's impression of what they saw. This is a lensing effect of gas clumps that are rotating around the black hole. Of course, they could only imagine that something like that would happen, but they were ready to observe. If there was something observable, they were ready for it, and they got this type of an image. there is a inner radius of the, what they call the accretion disk. That's all the material that's going whirling around the black hole. There's an inner radius. If you go in further in, matter, that's mass, cannot be stable. It will go into the black hole. It's not the event horizon, it's further out. So ISCO. And this gas clump that caused this flashing effect was orbiting. They could reconstruct very close to the minimum range that matter can orbit at about 30% of the speed of light. So this is very difficult to explain for me. I don't know more than what I've just said. But they have zoomed in now on the data of the details of the supermassive black hole in our own galaxy. The mass and the orbital period is 11.5 minutes, the spinning rate. And the radius of the event horizon is only 50 times the radius of our sun. And the proton sphere, that's where protons can orbit, it's 20 times. So they have really zoomed in now on the details of our own supermassive black hole, if you wish, in our galaxy. This is a major account. If you want to find scientific papers about this, then you can click on these references. So I need to move on. Just a view from the top, coming back up on the top of Paranal. This is a view towards the ocean, towards the west. There's cloud cover, but you can see the ocean. There's actually a condor flying there. He had a great time because there was such a strong wind. There was an updraft and he was having a great time. Condor is the South American eagle. And then if you turn around 180 degrees, you see this. And the guy pointed out that this volcano you can see here is in Argentina. So you actually can look the width of Chile from the mountain. The other thing which is really interesting is this hill here. It has a flattened top, and that's man-made. They are building the foundation for the ELT, the extremely large telescope there. So that's going to be the next generation, and it's going to be the neighbor of Paranal. This is an artist rendition of, as it were, on that hilltop, and in the distance you see Paranal. This is a 39-meter telescope, and they're building it right now. It will be operational somewhere in the second half of the next decade, like 25 or a little bit later. There are several 30-meter type telescopes in construction, or maybe already original or operational. I'm not totally aware off the top of my head, but this is going to be the biggest one. It's planned for any time in the future. So yeah, ESO is doing a lot of stuff there. San Pedro. This is in the far northeast here. It's a very picturesque little town. It's beautiful. Even for that, you will want to go there. It's like a Mexican village or something, but there are no gunslingers there. It's really peaceful and very friendly people, and a lot of tourists. This was middle of winter, but it's probably the best time to go there because midday we had something like 20 degrees Celsius. At night it's bloody cold, it's freezing, but the motels where we were, they had good bivets and blankets. It was fantastic. But the vicinity there, I need to go to my. This is a bit of the geophysics of Chile. San Pedro is kind of here. It's actually the Alma Observatory is very close. You see this major subduction here. This is one of the biggest subduction zones in the world. Probably the biggest one is in China, the front of the coast of China on the Japan. But this is I think the second, about 5 centimeters per year, I would guess. That's why they have these huge earthquakes in Chile and also tsunamis. Imagine that if there's an earthquake there at that subduction zone, you then have no warning time. There's an immediate tsunami coming. If you zoom in, especially the satellite image, you can see I call it tortured terrain. It's really, this is compressed in all kinds of ways. If you zoom in here, I'm not doing it now because of time. If there's time afterwards, I can do it. You can actually see the Alma Observatory, which is a whole array of 66 radio antennas, the famous millimeter array, also operated by ESA. You can go there on tours, but only to the control buildings. The actual telescopes are further up the mountain. That's 5 kilometers altitude. You would need oxygen to go there. This is San Pedro here. I want to show you two things. One is this area here. They call it Valle de Luna, Valley of the Moon. How do I get out of this? This, by the way, is the entrance, the driveway towards Alma. I found it a bit of a resolution. This looks like a derelict station or something. This is the entrance to the best millimeter astronomy observatory in the world. When we were driving from Calama, that's where the airport was, towards San Pedro, we came over a ridge and this is what we saw. And we were absolutely speechless. The terrain. See the volcanoes in the distance? If you have a subduction zone, you will have what they call back arc volcanism at a certain distance that we have in the North Island. We have the Camarac fault line in the ocean, east of the North Island. We have the volcanoes. That's textbook geophysics. And here are the volcanoes in some, partly in Chile, partly in Argentina, related to that subduction zone. But look at the whole terrain. It's really out of this world. You imagine that you're on another planet. Here's a diagram I saw in one of the stations which we visited. It's where they have salt flats. They didn't show the subduction here, but there's a lot of compression going on, and there seems to be two major ridges of uplift and depression in between. Here we are in that area of San Pedro. There's briny groundwater coming from under the ocean, from under the volcanoes, filling this the valley here. It's very high in salt, basically just sodium chloride, table salt, but it's also rich in minerals like boron and lithium. They said that 3/4 of the lithium that we use in the world comes from there. Anyway, first, the Valle de Luna. Okay, these are some pictures we took. You have to buy a ticket. You can drive a one-way road and then, or a dead-end road, and you go the same way back. This is the type of terrain you see there. Yeah, photographs don't even really do justice. It's amazing. They shouldn't call this Valle de Luna. It has nothing to do with the moon. This is Valle de Marte. This is Mars. This is a fantastic analogy of Mars. I've seen so many photos of Mars from the rovers. This is almost one-on-one. And there's not a blade of grass growing. It's totally, well, sterile, I wouldn't say, but it's there's no vegetation of any sort visible. In this wider area, they test rovers. I've read about that in that kind of terrain. Yeah. So if you want to go to Mars, this is your closest sensation. It's absolutely fantastic. This was the end of the road where you see all the salt. I picked up a little. It's all broken up. It has about 1.5 centimeters, or 1.5 centimeters of pure salt, and then on the crust of dirt. Amazing. The next thing, that's the last thing, is the Chaksa lagoon, they call it. There they have these lakes. So this is the real salt flats where they have flamingos. So these are shallow lakes, and there's a very simple food chain there. There are bacteria that grow there in that highly salt environment. And there's a kind of krill, small kind of crayfish, or what's the word, shrimps, feed on the bacteria, and the flamingos are there to catch the krill. There's another reserve further up the mountain which is known for the flamingos, but we found them here, and especially my daughter, she was absolutely delighted and saw our flamingos. Okay, final thing. I just want to throw in a tiny little bit of mythology. When I went to Chile, my first trip to Chile and even to South America, it's the only continent I've never been, I wanted to know at least something about the pre-Columbian history of Chile. And the second day still in Santiago, we went to the Museo Chileno de Arte Precolombino. Just one object that I found there, and that's the way I end my talk. Before I do that, this is a picture I couldn't let go of, and I waited something like 10 minutes before all the people were out of the way that I finally could take the shot. This is Rembrandt. That's my favorite painter. Sorry, I'm Dutch. He worked with light. He was the first one who really worked with light. This is totally Rembrandt. And I saw these two girls playing on a rock, a flat rock, which is set in the middle with the spotlight on it. And those wonderful statues, they're timber statues, wooden statues in the back. So this is Rembrandt. This is a permanent exhibition, if you ever go there, about Chile, ante-Chile. That's Chile before Chile. It's the history of before the conquistadores came. We found this object. That's my final thing. This is a serpent, and it's a lizard. And the text that goes with it is that the Mapuche, which are the indigenous people, they believe that the oceans were angry sometimes. Those are the tsunamis. Typically for humans, they can't explain anything. They feel guilty. That's something that we have done to the ocean, that is angry. But then there's the fight between the ocean and the continent, the land. The land is uplifted to give the people a chance to save themselves from the tsunami. That is basically the genesis story of the Mapuche Indians. That's what I understand from this. And this shows that this geophysics, this subduction and the earthquakes and the tsunamis that has been going on for eons, that will continue for eons. Of course, that was their reality. That is their story of the origin of Chile. So, yeah, I thought that I should throw this in to finish it off. Thank you very much.